So I think it's pretty important for us to talk a little bit about this before we look at kind of our topic for the day, and that is tangent lines with polar stuff. So let's review really quick. Let me go back just a little bit to some of these graphs that we looked at. Those right there. So I guess what I want to talk about is this, like what the slope of the tangent line is. And I think there's a temptation to get confused about that. So you look at these polar graphs, and very often a polar equation or polar function is going to be expressed as r equals blah 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 theta, right? So I want you to think about this. We could do a lot with this. There's a lot of different things we can do with it. We could find dr d theta, couldn't we? If I just did dd theta of one of these functions, for instance, maybe I'll just do it this one right here. So let's say I've got r equals 1 plus 2 cosine theta. I could do dd theta of that whole thing. And if I did, let's think about what would result. I would get dr d theta is equal to 0, minus 2 sine theta. That make sense? Okay. So, that's not that hard to do. I'm sure you guys could have done that without my help. But let's talk about what it means. Dr d theta specifically. It's not dy d anything or dx whatever, d something dx, specifically dr d theta. So if I asked you, if I told you, hey, dr d theta equals whatever, and then I said, what does that mean? What would you say? What do you think the graphical meaning of that is? It's actually not. Actually not the slope of the tangent line. Think specifically about the letters r and theta, what they mean, and then think about what that would mean in terms of dr d theta.
Is it the rate that r is changing as theta changes?
Yeah, it's the rate of change of radius with respect to theta. Okay, so let's go with this just a little bit. So let's do this. Let's think about the graph again. This graph was the little looped limacon thing, right? So I'll try to reproduce this graph. Something like that. I don't know. So let's see here. If I were to draw an angle in, let's say I was going to say, start right here at the origin and draw in that angle right there, or maybe, let's do something like that. Would it be fair to say that angle is like pi over 3-ish? I've done an okay job representing that. So here's what I want you guys to try to do. Hey, I want you, use your calculators, do what you got to do, and figure out what dr d theta is when we're pointed at the direction pi over 3. Okay, so in other words, you don't even need your calculators. You do this with unit circle. You can use your calculators if you want, but dr d theta at theta equals pi over 3 equals what? I think it ends up being a decimal. I think you get the root 3 in there. Let's see here. Yeah, because the 2's would cancel, right? Yeah. So negative root 3. Okay, fair enough. So let's go back to what Tess just said a second ago as far as what's the meaning of dr d theta. It's the rate of change of radius at, with respect to theta, right? With respect to an angle. So if we did this right here with these actual numbers here, dr d theta at theta equals pi over 3 is equal to negative root 3, how could you interpret that? What's happening when theta equals pi over 3? The radius is getting smaller or shorter, right? So you could also say, like you could word that a little differently. You could say that the graph of that curve is getting closer to the origin, right? Since the radius is shortening at that point in time, then if a particle were traveling around this, you could say around this curve here, you could say that the particle is getting closer to the origin at that point in time. That makes sense? And you could, of course, calculate this at any angle, right? Pi over 4, 7 pi over 3, or whatever it happens to be. And you could make a judgment based on that. But what I want you to understand here is dr d theta is not the slope of the tangent line. So if I were to think about a tangent line on a graph like this, we could say, the tangent line would look something like this. At that angle, at least the way that I've drawn it, the tangent line would look, I don't know, something like that. Roughly, be just barely touching the curve at that point, and mimic the slope right there. So based on what we just talked about with dr d theta, can you see how dr d theta, while it might be valid, is very different than thinking about the slope of the tangent line? It's not describing the same thing at all. And so that's what we're going to investigate today. Like, how do you actually find the slope of the tangent line for these kinds of things? It's not just a matter of, hey, do a derivative. It's a very specific derivative. And that's going to give us a very specific meaning. That makes sense? Okay, so let's go ahead and look where we're supposed to be looking, I guess, here this morning. So that would be back to here. And let's take a look at slopes of tangent lines and tangent lines with these polar graphs. So, no matter what your variables are, whether it's got t's in it, like when we did parametric and vector, or whether it's got r's and thetas in it, like we are dealing with right now, slope of the tangent line always is dy dx. Always, always, always dy dx. It'll just come down to how do we relate the t's, the r's, and the thetas, and the whatevers we got with y's and x's. It's going to come down to how do you establish that relationship and then proceed from there. But the end result, at least for a slope of a tangent line, is going to need to be dy dx, because we're always going to be graphing on the y-axis, the x-axis. At least we're in 2 dimensions. It's going to always be that. So let's remember, you can flip back in your notes a little bit, but there is a way that you've already seen. We haven't really worked a whole lot with it until now. There is a way to relate x's and y's and r's and thetas. So look back a page or so in your notes to remember this, but let me know once you've found it. How could we relate x's and r's and y's and thetas and all that stuff? Right, and y equals r sine theta. So that's going to be kind of where we start off with this, to say we know this relationship, and there's a number of ways you could say you know this relationship. If you ever had a physics class, you probably see this. If you remember converting, in pre-calc from like a polar idea to a rectangular idea, same kind of thing. And that's really what we're doing here, right? We're taking r's and thetas. Oops, I wrote that wrong. It should be r sine theta. We're taking r's and thetas. We're converting them into x's and y's. So that's where we're going to kind of start here. So the key is being able to remember that relationship. But this, I want you to say that's half the battle. That's way less than half the battle, okay? You got to start there, though. So what I'm going to say then is, see if this looks familiar to you. Just from a basic concept, say dy dx is going to equal dy d theta over dx d theta. It is. It's exactly like the parametric derivative, except instead of t's we have thetas. Now, theta is going to kind of function as a time unit, more or less, here. Why what? So that's a good question. So if you think back to the graphs, I don't want to erase this, but if you flip back in your notes to all those polar graphs we did, with just a couple of exceptions there at the start of like some somewhat unique graphs, weren't all of the r's set equal to something that only had thetas in it? So r equals 1 plus 2 cosine theta. R equals 5 cosine of 3 theta, that kind of thing. And so that r that you see there, the r cosine theta and the r sine theta, that r will be in terms of theta. So it's going to be x in terms of theta, y in terms of theta. So when you differentiate, you can get dx d theta and dy d theta.
So will you solve for r and y?
Well, typically they're already solved for r, right?
But but if you differentiate, will it be r d theta?
If you did what?
If you differentiate,
We're not going to differentiate that. We're simply substituting here. So I'll give you a for instance. Let's say that the function we were working with was, I don't know, r equals 3 cosine of 2 theta. Let's say that was our function. We're going to be trying to find the equation or slope of a tangent line for that. Hayden, does that make sense? What we would then say is x equals 3 cosine of 2 theta cosine of theta. I'm going to erase all this in a second. And y equals 3 cosine of 2 theta sine of theta.
How can you do that?
Because you're saying y equals r sine theta and r equals 3 cosine.
So it's a substitution. I'm replacing the r with what the r is equal to.
Yeah, but r is equal to 1 over sine.
Why are
Pi
you
over sine theta. So how did you?
Why are you trying to solve for r? You seem pretty fixated on solving for r. I don't think we want to do that. So, Hayden, let me explain why. Or I'll wait until whatever is twirling around in your mind stops, because I don't think you're going to hear me until that stops. But I'm not going to wait forever, so make it stop.
Wait, I think. No, my way.
I have no idea what your way is. Hey, let me.
Well, it's the same thing what you did, but I'm just, with these equations you gave up top, I said r equals y over sine theta, and then if you say y equals, and then you put that in for r, and then you times by sine theta, and you get that.
What's your goal to do?
So you have y's instead of r's.
Yeah.
I'll end up with
You don't
that.
have any y's. I mean r's.
I don't have any r's in mine either. X equals 3 cosine 2 theta cosine theta.
You can do, but that's not in the same form.
Yeah, it is.
Yes, it is. This right here. So I told you, I made up an equation, granted, I just made it up on the fly. I told you that r equals this. So what I did then is in this equation right here, wherever I saw an r, I put that. And in the other one for the y, wherever I saw an r, I put that. So I substituted.
You can't put, but what is r equal?
R equals 3 cosine of 2 theta. I made it up. It's just a made up function at this point.
I just said the opposite.
I think I see what you're saying. That's why I kept on saying, what's your goal? Because I felt like our goals were the same, and you were arguing so passionately that I couldn't do what I was doing. And I'm like, yes, I can, but I think we're going to the same place.
Yeah, okay, I understand.
That make sense? Okay. So, the bottom line is, I'll just reiterate, the bottom line is we want to have basically x in terms of theta, and we want to have y in terms of theta. And the reasoning behind that is our ultimate goal here is to find dy dx. And if we don't have y's and x's in terms of theta, we're not really going to get there. Okay, so I'm going to take it a little bit further, and I hope this is okay. And this kind of piggybacks off of what I was just talking about there with Hayden. Isn't r, from all you've seen, isn't r typically some function in terms of theta? Some function in terms of theta. So I'm going to take this one step further, and I'm going to say x equals f of theta cosine of theta. That okay? And y equals f of theta sine of theta. I'm just replacing the r with what the r is typically equal to. It's equal to something blah, 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 theta. So I'm just going to say, all right, it's some function in terms of theta. Is that okay? Okay. So what brings this to a challenging spot is that both of those are products. And so if if our ultimate goal is to get dy dx, we're going to have to do dy d theta. We're going to have to do dx d theta. But in order to do that, we're going to have to do a product rule. Here's what that would look like. So if I'm going to say dy dx, bless you, if we're going to say dy dx equals, my numerator has to be dy d theta, so I'm going to differentiate the y in terms of theta equation. So it's going to look like this. 1 d2 plus 2 d1. That make sense? Okay. And then dx d theta is going to be similar, except we're going to be using the x equation. So it's going to be 1 d2 plus 2 d1. Okay, and that's it. So a couple of questions I'll ask for you, because I think they're worth asking. Number one, do I have to memorize that? No, you definitely don't. In fact, some people might find it beneficial to memorize that. I think the vast majority of you will probably say, you know what, I'm just going to sort of make a custom derivative for everything that I come across in these sorts of situations and not worry too much about the situation as far as memorizing it goes. But you certainly are welcome to memorize it, and if that works for you, then do it. It's okay. Memorizing it, could be a benefit if that's how your brain is wired. Secondly, does anything cancel? No, nothing. There's temptation, some just horrible temptations to do crazy stuff, right? So temptations to be like, oh, cancel, right? Just made this thing way easier. I mean, Mr. Anderson, you're making it so much more difficult than it needs to be. Yeah, no, you can't do that, of course. Another question, could we do some trig identities and make this a little simpler? Like, why can't this just be negative cotangent theta or something? I mean, again, similar reasons. You can't pick out little parts of a sum or a difference and pull those out. It just doesn't work mathematically. You all know this. But I bring these things up for a reason, right? Because I've seen good math students like you say some crazy stuff later on. They're like, man, I can't believe I said that. So I'm just bringing it up ahead of time. That's pretty much it as far as the formula goes. And you'll see as we do a couple of these, you'll kind of see, okay, yep, I see kind of that form coming through there. I show this to you simply so that you're not shocked when you see the size of some of the derivatives that we'll do later. Because the product rule just makes things expand beyond what we would normally expect. Okay? So I show you that, say, we're going to try this first example, not trying to import this formula into it by simply kind of recognizing that that's the type of thing that will happen. So let's go ahead and move forward to that next page, I think. Would be a good place for us to go. So thinking back, let me just refresh our minds about this. Thinking back to the idea that dy dx equals dy d theta over dx d theta. What do you think would cause a horizontal tangent line? Say one more time, Jared. It's actually the other way around. We want the numerator to be 0. So I'm going to put it like this. To answer the question right there, I would say what would cause a horizontal tangent line if dy d theta equals 0 and dx d theta does not. Okay, so if dy d theta equals 0, but dx d theta does not equal 0, then wherever that angle is, wherever that direction is that you're pointing, you should have a horizontal tangent line at that spot. And then what do you think would cause a vertical tangent line? Yeah, just switch around the logic here. So it'd be when dx d theta is 0, and at the same time, same place, dy d theta is not 0. Okay, so
Wouldn't it not really matter if dy d theta equals 0 if dx d theta still equals 0?
it kind of does actually. So and the reasoning would be this: you'd have a contradiction, right? So if dy d theta is 0, that would seem to clearly indicate a horizontal tangent line, right? Dx d theta being 0 would indicate a vertical tangent line. The one scenario we haven't talked about yet really is, we've seen it on one graph or the other, I think, the sharp point concept. Typically when they're both 0, you won't have a horizontal or vertical, you'll have a sharp point where there is no tangent line slope. So it is really kind of 3 unique situations. And so that's why we have to consider both. Good question. Okay, so and the final statement here before we do our example is if dx d theta and dy d theta are simultaneously 0, then no conclusion can be drawn about tangent lines as far as horizontal or vertical. We could perhaps look at a graph and be like, hey, it's the sharp point thing, and kind of see that, but we can't make any judgment beyond looking at that graph and seeing what's actually happening. So you guys ready for our first example? Okay, we'll take our time here, and this is where your old friend the unit circle is going to be your friend. This would be the type of thing we can do without a calculator, and frequently that's how it'll be, hopefully successfully. Okay, first thing I want you guys to do, first thing we should do, is just so we can kind of understand what's going on. You don't always get this, but I think starting off this is good. Take your calculators and let's graph this. R equals 2 parentheses 1 minus cosine theta. Just get a sense of what it looks like. And I think it's going to be a cardioid, right? This will have a sharp point, won't it? Let me know once you get it. I'm just going to peek here and make sure I remember. Yes, it is a cardioid going left. Okay. You call it a lily pad? Okay, you can call it a lily pad if you want.
Because like a heart has a sharp point on both ends. And that does.
Hey, that is, whoa. I'm glad I'm recording this video. That was just freehand. I feel, compared to all my terrible graphs, that was pretty good. I'm really stoked about that, yes. Come on, it's the little things in life you got to get excited about. All right, so does that, please tell me that looks like your graph because I don't want to erase that. Okay, so we've got this cardioid thing going on, and so what I think the value of seeing this graph before we do anything is we can get a sense of where we're going to see these horizontal vertical tangent lines. Just looking at this graph at a glance, how many horizontal tangent lines do you see? 2 of them. Yeah, I would say that seems right. So down here and right there, those look like those would be roughly locations for horizontal tangent lines. And then how many vertical tangent lines do you see? There's 2. We probably have 3 different angles that have vertical tangent lines. And, there's going to be one out here, one right here, and one right here. But because of symmetry, I think those 2 short ones on the right will probably be the same line.
I have a question.
Yeah.
Is it still a tangent line if it touches 2 points?
Is it still a tangent line if it touches 2 points? Yeah. So the tangent line, what we're looking at here is it matches the slope and intersects in one point. These are truly two separate tangent lines. They really are.
But if you keep on going, you'll touch 2 points. So
I understand that.
I
I get that. I want you to think I'll use the board for this, but we've actually seen this before and you didn't make the same argument. So let's address the question at hand. It says, find all locations of horizontal vertical tangent lines. We could probably visually estimate that, but we want to find exactly what they are, and we're going to have to use the derivative to do that. So let's do this. Let's start off here. I'm going to just get ourselves set up with x's and y's. I'm going to convert my polar equation into x's and y's. Sorry, I got to fix my little stand here. I think, there we go. So I can say this. I can say x equals r cosine theta. So I'm going to go ahead and plug in what r is. So I'm going to say x equals 2 minus 2 cosine of theta. That's r. Cosine of theta. X equals r cosine theta. And then I can also say y equals r sine theta. So that would be 2 minus 2 cosine of theta sine theta. So again, my goal here is very simple. I want to have x in terms of theta and y in terms of theta, which will enable me to find my dy dx. So I want to make sure that first step seems logical. It'll be a very common first step. Okay. Maybe we distribute. I don't think that it's, I don't know. Take a quick vote. You want to distribute or not? It makes little difference other than your personal preference. Distribution. Okay, we're not distributing. That's fine. Okay, so what I'm going to do now is I'm going to attempt to find dy dx. So put these two together, and we're going to say dy dx equals dy d theta in the top, dx d theta in the bottom. So I'll write that here, and then we'll try to write specifically what that is for this problem. Okay, so dy d theta is going to involve the product rule. The xt theta is going to involve the product rule as well. Why don't I work quietly up here? You all know how to do this. You work quietly there. We can compare notes here in just a second. Right, and kind of small up there. Does that work for you guys? Okay. Obviously, there's some cleanup work that could be done. I don't know if it should be done at this point. But that's it, right? That's dy dx. Who knew it could be like that? And there's a lot going on there. But simply, if you can handle the product rules, you're in pretty good shape. We'll do some cleanup work in a little bit. But for now, is that okay? All right. It's going to get a little more interesting. I'd love to challenge you guys. I hate it when you're bored. So get challenging, a little more challenging. So now we're really equipped to answer the question, right? At this point, we've got the tools we need to answer the question. Let's go ahead and try that. So it says, find all the locations of horizontal and vertical tangents. We know from earlier, horizontal tangents will happen when dy d theta is 0, vertical when dx d theta is 0. But if we get 0 at the same angle, then we kind of have to say, we don't know what's going on there. Maybe the tangent line doesn't exist. So let's see here. What do I want to do? You want to start off with difficult or easy? Difficult. All right. So let's find locations for horizontal tangent lines. Okay. So I'll label this. You don't really have to do this, but I'm going to say the following is an effort to find horizontal tangent lines. Here we go. I'm going to simply take the numerator and set it equal to 0. So I'm going to say, and is it okay with you if I do a little multiplication while I set equal to 0? Like I'll distribute the cosine and multiply the sines. So that would be 2 cosine of theta minus 2 cosine squared theta plus 2 sine squared of theta equals 0. Couldn't I say what?
No,
I'm sorry?
one's negative, so I'm thinking trig identity.
Oh, don't worry. Your wishes about trig identities will be fulfilled soon. Don't worry at all. Distributive properties, some multiplication, not that big of a deal, right? But now we've got this trig equation we need to solve, and no calculator. Calculator is present, then, okay, this gets, pretty simple. No calculator present, this is a little more challenging. So we have a problem here, we have an issue here, and here is the issue. I've got a trig equation, and if you look carefully at it, you realize pretty quickly that you have 2 different types of trig functions. Cosine and sine, right? Not good. Without the calculator, that scenario is not good at all. We need to figure out a way to transform this to be all sines or all cosines, and then we can go from there. So, do you have any ideas? Like, what could we do? Yeah, Sydney. Using the Pythagorean identity, yeah. So, let's try that. Let's see what happens. So, we'll replace, and you specifically said replace sine squared with 1 minus cosine squared. Okay, so we're going to say 2 cosine of theta.
Just divide by 2 for all of those.
Yeah, we sure could. You want to do that right now? I'm down with that. Okay, so let's do that. Let's mentally divide by 2. So we'll go cosine of theta minus cosine squared of theta plus, remember all the 2's are gone, so we're going to replace the sine squared with 1 minus cosine squared.
Isn't it cosine squared theta plus sine squared theta?
Yeah, but like you said, so they would then.
I'll erase this, but I think that's worth a question. So this is the basic Pythagorean identity based on, the right triangle, Pythagorean theorem, unit circle stuff. And so I think what Sydney was just saying and what Devin was saying there is just subtract that to the other side. Or that's what we're doing here. We're just subtracting the cosine squared to the other side. So sine squared equals 1 minus cosine squared. Okay. All right, so we have definitely eliminated that issue we had before of having a mix of sines and cosines. Let's clean this up. And let me encourage you that the fun's not quite over yet. There's still more fun to be had. So what I'm seeing here is negative 2 cosine squared theta plus cosine of theta plus 1 is equal to 0. So, in your wise math eyes, what do you see? A quadratic. Do you see it? It's not as obvious as some, right? It's not x squared plus 2x plus whatever. It's the inputs are cosine thetas instead of just x's. Again, I'm not saying this facetiously, using like your wisdom in math, what might be a wise, like minor little move that could make this easier for you? Do what with a 1? Divide by negative 1. In other words, change all the signs, right? We want that a value to be a positive. That's just because we're used to that. If all of our teachers had told us, hey, we want a to be negative, then maybe you would feel differently. But I think I would just divide or multiply through by that negative 1. So it'd be 2 cosine squared of theta minus cosine of theta minus 1 equals 0. Now, absent a calculator and not wanting to run this through the quadratic formula, maybe, I don't know, you could. Factoring might be the way to go. One way or the other, we need to get the cosine theta isolated and solve for. Does factoring strike you as a wise move? I think to me that feels faster than the other ones. Are you guys seeing the quadratic in there? Is anybody not? I want to make that really clear. Maybe for those that watch the video later, I'll make this a little more clear. This is a quadratic just like this. Right? Except instead of an x, it's cosine theta. So if we could factor that 2x squared minus x minus 1, then we should be able to factor this as well. So, okay, so factoring. Factor is a product of two binomials. And let's see here. Well, one of them is going to be 2 cosine theta. If this is going to work, it's going to be 2 cosine theta. The other one's going to be cosine theta. And I'm going to go with minus 1 there and plus 1 there. If you do a little bit of guess and check, you can see that. Okay. Hasn't this just been like one of those movies with like twists and turns all over the place? There's one more twist at the end. So we set each factor equal to 0. We say 2 cosine of theta plus 1 equals 0. And cosine of theta equals, or minus 1 equals 0. I'll just say equals 1. The one on the left, we go to cosine of theta equals negative 1/2. The final twist on this first half of the movie is a unit circle, right? So cosine of theta equals negative 1/2. So for 0 to 2 pi, what angles have a cosine?
Pi over 6.
Say again?
5 pi over 6.
5 pi over 6. Let's see here. And cosine, I always have to build my little triangles in my brain. So let's see here. No, I think it's going to be an over 3, right? It's to be a 60-degree angle if we want to live in the degree world. But it's negative, right? Where's cosine negative? Isn't it negative in the second and third? So 2 pi over 3 and 4 pi over 3, right?
No, because I plus pi over 3.
So I think for horizontal, I'll just make my list up here. I'm going to say horizontal happens at 2 pi over 3, 4 pi over 3, and where is cosine of theta 1? 0? And just 0, right? 0 and 2 pi. But you're either going to include 0 or 2 pi. but not both, right? Okay, so we'll say just 0. Okay, so that's my tentative list of horizontal tangent line locations. So I told you that was like lots of twists and turns in the first half of the movie. The second half of the movie has fewer twists and turns, but still a few. So I'm going to do this on the left side, or the right side of my page here. Like I said, I hope you wrote small, or small enough, I guess, I don't know. So to find potential vertical tangent line locations, we need to set, as mentioned earlier, we need to set dx d theta equal to 0. So this is my attempt at vertical tangent lines. I need to note to self, I need to give myself more room on these notes. I have a feeling that I've made that note to self before and just forgot. Okay, so here we go, denominator. Once again, I'll distribute as I go about this. So it's going to be, you can do the same thing if you want. I'm going to run into my graph here. I don't like that, but we'll survive. Okay, so I multiplied a little bit, distributed there. And I think I got things squared away. Does that make sense to you guys? Set the dx d theta equal to 0. A little bit of cleanup work here. -2 sine of theta plus 4 sine of theta cosine of theta equals 0. If you add those two like terms up, 2 plus 2, of course, is 4. Okay. Say again? We sure could. We sure could. That'll be. Let's do that now. That's fine. So if we divide by 2, we end up with negative sine of theta plus 2 sine of theta cosine of theta. And some of you that were good at trig identities might be seeing a trig identity here, but we don't want to go there. Because remember, our ultimate goal is not to do trig gymnastics. Our ultimate goal is to solve. So at this point right here, that's why I said, did you want to start off with easy or difficult? And we started off with difficult. This one's a little easier. Factor it out. Yep, factor out a sine. So you factor that out, you end up with sine of theta times -1 plus 2 cosine of theta is equal to 0. And set each factor equal to 0 and solve, right? So sine of theta equals 0. And then if we do the, a little bit of solving in our heads as we go here, it would be cosine of theta is equal to 1/2. So, final little twist in this story, on this side at least, is, the unit circle. So where is theta, for what theta is sine 0?
0 and pi.
0 and pi, good. And then for the other one, for which theta is cosine, 1/2. Pi over 3 and 5 pi over 3. So, really the same angles as the ones we had before, except they'd be in the first and fourth quadrants. Okay, so now we make our list. We say, all right, well, the angles for what theta do we get vertical tangent lines? We list them out. We say 0 and pi over 3 and 5 pi over 3. You guys good with that back there? Okay. So what is the one thing that jumps out to you?
Zeros, they're both ones.
0 shows up in both lists. So that means when theta is 0, then both dx d theta and dy d theta are 0. And that's that one case where you said, hey, we can't actually draw any conclusions about that. So what we need to do then is eliminate those from our lists. That actually happens to be the sharp point. When you're facing 0 radians, you get the sharp point. You can see that on the graph. And that's why neither would be included in the list of vertical or horizontal. Now, this does say, it's a little bit vague here, and we're not going to go there with this. It does say find locations And so if it said find locations, parentheses, x comma y, this would take on a whole new level of length, right? Because then you'd have to take all 5 of those angles, use your x equals r cosine theta, x equals r sine theta, and find the x and the y for each of those. I would say that that sort of thing would be very rare, simply because that would be an exhaustive list. And I want you to think about this. This problem has taken us almost to the end of class. This problem has taken us like 25 minutes or so to do. And so to add another like 15 or 20 minutes onto that of like careful trig without a calculator, now we're looking at like a 40-minute question or so. Probably not where we want to spend all of our quiz time, right? So we'll say those are the angles. And hey, listen, you can see them, right? When theta is 2 pi over 3, check this out. When theta is 2 pi over 3, we are looking at, right about there, horizontal tangent line, right? When theta is 4 pi over 3, right about there, roughly a horizontal tangent line. When theta is pi, right there, vertical tangent line, do you see it? When theta is pi over 3, that would be right about here, vertical tangent line. Finally, when theta is equal to 5 pi over 3, roughly there, once again, vertical tangent line. And then that double zero, as we pointed out, was that sharp point in the middle where there is no tangent line. So, all right, have a wonderful weekend. Nice work. Way to track with me. You guys did very well today. Look forward to continuing on with some polar activities on Monday.